Hey scholars, welcome to Math Savvy. I'm Steph, and today we are going to continue our series on real analysis, and we are going to cover all things metric spaces. We are mathematicians, so we have to define and explain everything in a deeper and philosophical way. And that is really what real analysis is. It's an extension of calculus, and we cover all of the concepts of calculus, like integrals, differentiation. And one of the most important topics of calculus is the concept of distance. And that is where metric spaces come in. So a metric space is a set together with a notion of distance, usually called a metric. And that is a function between elements of the set. And we usually refer to these elements as points. The greatest example of a metric space is the real space together with its usual metric, which we'll talk about. So as I said before, what makes up a metric space are two things, a set and a distance function. And what would the set be? Typically it is r squared with the usual distance function defined above as the absolute value of x minus y. And this is a formal way of writing a function here. It takes 2 points, x and y, and applies this function to get a one-dimensional real number. And quickly, here are 3 properties of what a distance function must have. So the distance function needs to be positive or 0. Distance function between x and itself is going to be 0. And if the distance function is 0, that implies that x is equal to y. Second property, for all 2 points, x and y, in the real space or a set x, whatever, the distance function between x and y is the same as the distance function between y and x. And this property is typically called symmetrical. The third property is very important. So for 3 points in the set, the distance between x and z is less than or equal to the distance between x and y and the distance between y and z together as a sum. And this is called the Triangle Inequality. So with that context, let's apply this to a more general definition of a metric space. Yay! A metric space is a set x together with a metric or a distance function. So these are the 3 properties that the metric space must satisfy. So firstly, positive definiteness. So for 2 points in the big set x, the distance must be positive. Secondly, the distance between x and itself is equal to 0. And if we have 2 points, x and y, in the big set x, and the distance between these 2 points are 0, then x is equal to y. Straightforward. The second is symmetry. It's kind of the same thing here. So the distance between x and y is equal to the distance between y and x. And then we have the third property is the Triangle Inequality written out here. And these were the properties that we saw before under the distance properties. There is no difference, but these properties are following what the metric is. So the metric is that distance function. And you are testing these properties based on the given x, or the given big set x. Does that make sense? Okay. I hope so. Anyways, let's look at an example. This one is going to be the easiest example. And that's why we're doing it, so we can get some practice in. So example 1, prove that the following is a metric space, and it's given our metric here. So the distance between x and y is 1 or 0. 1 if x is not equal to y. 0 is if x is equal to y. So this is called the discrete metric. And let's do it. D1, let's do the first part. So distance between x and y is greater than 0. Great. The distance could either be 0 or 1. That's greater than or equal to 0. Good. Ding. Next part. Distance between x and itself is 0. True. Pretty self-explanatory. if the distance between x and y is equal to 0, x is equal to y, and that is given in the given metric that we are trying to solve. So those don't require proofs. It is pretty straightforward. D2, so distance between x and y is equal to the distance between y and x. So we're going to use logic here. We know that x is equal to y if and only if y is equal to x. Pretty straightforward, so therefore that must be true. All right, so now we're going to do the triangle inequality. I'm going to write down what we know because this is going to be a little bit more of a lengthy proof. So what we know is the distance function, the metric. And there's two cases here, which I am going to test out both cases. This is just the type of proof that we have to go through every single possibility. So the first case, I'm going to do the distance between x and z is equal to 0. That implies x is equal to z. So then either if x is equal to z, then either x is equal to z, which is not equal to y, or x is equal to z, which is also equal to y. If we test out both of those cases, we see that 0 is less than or equal to 1 plus 1, which is true, or 0 is less than or equal to 0 plus 0. And that is pretty straightforward. So then let's do the second case. Distance between x and z is equal to 1, which is the only other possibility. And here it is a little bit different, so that would imply x is not equal to z. So let us write down the three possibilities that we can see here. So x is equal to y, but it's not equal to z, or y is equal to z, but that's not equal to x. Or they're all not equal. So then I'm going to write down all of these possibilities, given that the 2 points are equal or not equal, and we see that every possibility is true. Thus, D3 is proven. Great, so that is the first example. So as I said before, we do have standard metrics, and those have to do with the real space. We have r squared, r cubed, all the way up to rn, and those have classic metrics that are included. So we are going to review this in our next example. So we are going to cover the Rn metric space, and that is given by the square root of x1 minus y1 squared all the way up to xn minus yn squared. And x1, x2, x3, x4 are going to be the vector x. They're going to be components of the vector x. And you'll see what that means in a second. So firstly, we're going to do the first property. We're going to prove positive definiteness. So it is going to be greater than or equal to 0 because it is a square root. You could just write that down. That's all you need to show. That's all you need to say. So then we have the distance between x and itself is 0. So when we have a vector x, x minus x is 0. And that is because x1 minus x1 is 0, x2 minus x2 is 0, all the way up to xn minus xn is 0. So that just proves that x is itself. Kind of straightforward. If the distance between x and y is equal to 0, then x equals y. So we're going to start with the if part. That is what we know. The distance between x and y is equal to 0 implies that the square root of x1 minus y1 squared plus all the way up to xn minus yn squared, that's all equal to 0. I'm going to square both sides, and I'm going to get that x1 minus y1 squared plus all the way up to xn minus yn squared is equal to 0. This implies that x1 minus y1 is equal to 0, x2 minus y2 is equal to 0, and so on. We're going to expand this, so x minus y, the whole vector, is going to be equal to 0. You move y to the other side. Thus, x is equal to y. Good job. So I'm going to let you guys try the next property. Just pause the video, and in the next slide, there's going to be the answer, and we're going to talk about it. So, good luck. Welcome back, everyone. Okay, so here's our answer. This was pretty straightforward. We squared both sides. We subtracted every term on the right-hand side, put it on the left-hand side, and then we noticed that everything canceled out. Easy peasy, lemon squeezy. Okay. Now we're gonna do the third property. Okay, we're gonna rewrite this. So we are gonna write it as the sum of the square root. I didn't write it here, but you'll see in a second. Sum of the square root of x1 minus z, or xi minus zi squared, and so on. So we're gonna try and prove that this is true. In doing so, we have to use the Cauchy Schwarz inequality. And let me introduce that to you guys. Okay, now we're going to do some substitutions here, my friends. The sum between ai squared, sum between bi squared, etc., etc. And I added the square roots here, so I didn't forget. Didn't forget. Okay, pause scholars. What I did here was introduce the problem. The second statement there is exactly what we are trying to prove, and I introduced a tool that we are going to use in this proof called the Cauchy Schwarz Inequality, what I put in green. And then finally, I introduced some substitutions to make the proof look a little bit cleaner. And let's move forward from there. Thanks, homies. Next slide, we're gonna just move forward and not use the I equals 1 to the n, because that's just gonna waste us some time. So I'm gonna continue this statement, and we're gonna square both sides. So what we get is that extra 2 times the square root of the sum of bi squared, the square root of the sum ci squared, all multiplied together. Using that Cauchy Schwarz inequality, we see that that term is greater than or equal to the square root of the sum bi ci squared. And that is beautiful. We can use that, you guys. We can substitute that in. And it's going to be less than or equal to. Because the square root of x squared is equal to the absolute value of x, we see we can just put the square root of that sum squared, and that is equal to the absolute value of that sum of bi ci. Great. So let's plug that in. What we get is the sum of bi plus ci squared, because that is now a factorable expression. And that's kind of where we saw ourselves going here, because when you get two terms that are squared, you just kind of want to manipulate the function until you get that factorable expression. That's most of the time going to help you out. So what we get is that's equal to bi plus ci squared, the sum of. And finally, we can plug everything back in. We see that the y's cancel out. And finally, the right-hand side is equal to the left-hand side. And that's all we wanted in life. So that's all we had to do. That did seem a little bit more complicated. There are tricks that we just need to practice and get through, but that's pretty much all we need. So that's all I have for you today, scholars. Make sure you like and subscribe and leave a comment of what you want us to cover in any of our videos. We are open to suggestions, and check out our tutoring service, you guys. We are doing online tutoring, and we are very good at what we do. Hopefully, we've been told that we are. Anyways, love you.